7.4 collisions in 2 dimensions. So let's go over system conditions. Like last time, no impulse applied, the momentum is conserved. This one's pretty easy. Before we use the formula MVO, or yeah, MBO is equal to MVF. But now we'll do something a little bit different, and we'll break this down into components. So before we were doing something in one direction. So let's say that this is initial velocity, and let's say that this is the initial velocity of the system afterwards. Well, I guess that wouldn't really work with the one-body system because the initial and final velocity should be the same. So let's make this a two-body system. So it's going to be m1 plus v2 plus m2 BO2 is equal to M1V F1 plus M2 VF2. So yeah, there's the logic there. So if we assume linear momentum is perfectly conserved, we can, let's just say that the velocity of the first body is here, and then the velocity of the second body is here for the initial positions. So I'll just say 0, 0. For the final positions, let's say that it's this and this, or something like that. We just have to break down the x components because, again, momenta is a vector quantity. So you can just break this down into vector quantities such that it will be mv1 vox1 plus m2 vox2. And it's a little bit complicated, but VO just means initial, X just means in the X direction, and so on and so forth. So in other words, we just break down the velocity into vector components, whereas before we were not dealing with scalars per se, but we were dealing with them in one dimensions. Much like kinematics, you always break them down into 2 dimensions just to ensure that there is no overlap and that you can do it in a 2-dimensional field. That's the logic here. Again, same thing here, just resolving vectors multiplied by mass to get linear momentum, because Vx times Vx times m will give you the linear momentum in the x direction. So